Hello. In this video, I'm going to introduce the normal distribution. As I said at the beginning of this slide, the normal distribution is the most important distribution in not only in statistics but in science in general, right? The single most important distribution family. And examples. Interestingly, many phenomena in natural science follow a normal distribution, like heights and weights of animals and plants are amazingly close to a normal distribution, normally distributed. And velocities of the molecules in the ideal gas, I don't know what exactly it means, uh, but I saw materials that like physics or in chemistry, many distributions are normal. So also in social science, normal distribution is commonly assumed. So we have to make assumptions to proceed the argument. And in that case, if you assume a strange distribution, people may not believe it, but normal distribution is often acceptable, right? For example, standardized test scores. When you have test scores, it's believed to be a normal distribution. And also in finance, Black-Scholes equation. There is a famous equation called Black-Scholes. The economist Scholes received the Nobel Prize due to this contribution. So it calculates the optimal pricing for an option. So anyhow, doesn't matter what it is. But anyhow, what it assumes is that financial returns are normally distributed. Then what is the appropriate pricing for an asset? That's the that's what this equation is about. And also in management, in quality control, Six Sigma, there is a famous theory called Six Sigma. So that also assumes that the errors follow a normal distribution. By the way, the Six Sigma is invented by GE in the research center in our neighbor. So uh, that's why I'm using this as an example. Anyhow, normal distribution is so common and important and widely used, but I did not mention anything about statistics here. Needless to say that statistics uses normal distribution heavily. You are going to see that in the following semester and the remainder of the semester. You will see how we use normal distribution in statistical inferences. Um, Normal distribution has two parameters. By the way, it's like in the binomial distribution chapter, I derived the probability formula. It was complicated, but still it was doable. But in normal distribution, it is impossible. The the probability function is super complicated, and its derivation is more mathematical. So it's not from our like common assumptions like you try n times and there are the probability is p binary independence. It's not like these assumptions. It's purely mathematical derivations. So I'm not going to tell you how the probabilities are defined, but I will just give you the results. The result as a result, what's interesting here is the parameters for this distribution is mean and variance, which is very nice. You don't need to calculate mean and variance um, separately. So if you know the mean and the variance, then you may approximate to a normal distribution. Of course, the variance has to be strictly positive. And we usually write x follows a normal distribution with parameter mu and sigma squared. And because normal is so common, I will simply use n. So there is no other distribution that can use simply n other than normal distribution. Its graph is the bell curve. The density, probability density, looks like this, and the well-known bell curve is the normal distributions probability density function. And in this graph, I changed the mean with fixing the variance. The variance is fixed at 1, but mean is 0, 1, minus 1. So 0, 1, minus 1. What you can see here is it's a parallel shift. When you change the mean, only shifts the location. Shape does not change at all. And this is what happens when the variance changes 1, 2, or zero point 0.5 with the same mean, always centered around 0, but it's a matter of the dispersion, how concentrated or how flat, how widened. So typical bell curve shape you are familiar with. And to summarize, just a few properties, basic properties of the normal distribution. You don't need to memorize them. But anyhow, it's so nice. So just nice properties. All of them are nice. First, always symmetric. Normal distribution is always symmetric about the mean. So because it's symmetric, the median is mu, right? When it is symmetric, when you cut at the mean, exactly 50% on the left and 50% on the right. So it should be simple. And second, the probability peaks at the mean. The highest probability is where the mean is. So mean is the mode. If you remember how we define the mode, mode is the highest point. It's always the mean. So mean, the median, and the mode are the same in this example. And it ranges from minus infinity to infinity. Even if the probability approaches to 0, still it is not exactly 0. There is a very small probability as it runs down to minus infinity or to the positive infinity, right? It is not 0, but still but very, very close to 0. Anyhow, the range is infinity. So the range, it ranges from the minus infinity to the positive infinity. So the range is infinity, the infinity, and the minimum and the maximum do not exist. They are also infinities. Also, probability decreases away from mu. It's unimodal. There is only one peak, and it only decreases when you move away from the mean. So it smoothly goes down as you move out. As you move out, it goes down. Like so, there is no other peak outside the mean. And when you increase the mean, it shifts the curve to the right. And when you increase the variance, it flattens and widens the curve. As you see, the orange has the largest sigma, and the green has the smallest sigma. So this is how we like basic properties about the shapes of the normal distribution. And as I said, in the following chapters, all you need is a normal distribution. All random variables will be approximated to a normal distribution. But the problem here is that even though it has many nice properties, one big problem is it is not easy to calculate the probability. The probability formula is so complicated, so I don't tell you. And even if you know the density function, you cannot integrate it by hand. So first problem is density function is difficult. Cumulative distribution function is difficult, and calculating the area is not possible. So that's the first problem. And second, how do we fix the parameters? Even if you know the area or the CDF, or if you have a computer, you like when the parameter changes, you have to recalculate everything again. So these two problems make normal distribution less convenient, less useful. So that's the only problem we need to solve at this point. So we are going to first the second problem. Second problem is resolved by fixing the parameters. Among many combinations of parameters, I'm going to use 0 and 1 as the standard normal distribution. Standard, when I say standard normal distribution, it means one exact distribution with mean equals to 0 and variance equals to 1. And this is a special normal distribution, and alphabet Z is usually notation for a standard normal distribution. And we are going to use this notation in the following chapters. Z as a standard normal distribution. Remember this, you will see this a lot. So, okay, we will study the standard normal distribution first, and then how do we calculate the probability? We are going to take the CDF approach. Density function, calculating the area below the density function is even more difficult. So we are going to use the CDF approach, and after fixing the parameters, and before moving the course to online, I used to use a standard normal distribution table. I distributed papers. On the paper, there is a table, a lot of numbers that has CDF numbers. So the cumulative probabilities are listed on the tables. It was very outdated, frankly. There was no other clear option. But now we are online, so it's nice to have a calculator or a program or online web pages. So we are going to use Excel. I will, in a separate optional videos, I will show you how to use Excel to calculate standard normal distribution probabilities, right? Or you may use a different program, or if you type like standard normal distribution calculator on Google, then there are a lot of web pages. They calculate standard normal distribution probability for you. So we are going to consider this approach. And what we are going to do is here, this, like, so suppose that f is the CDF, cumulative distribution function of the standard normal distribution variable z. Then remember, the definition of the CDF is this: f of a of value a equals to probability smaller than a. That means if you input a into the calculator or table, then you will get probability smaller than a. That's what this function is doing. So now then it's a matter of changing a, right? So on Excel, I will tell you how to input a and get this probability. So, like for example, practice this. In the separate video, I will show you how to calculate these the first three probabilities. Then it is easy to generalize to the other values. So, and once you do this, you can put any numbers you want and you can get the answers. Okay, then I will stop the video here, and as I said, there are separate videos that demonstrates Excel, how to use Excel to calculate standard normal distribution probability. So, and next week we are going to use the standard normal distribution to approximate other normal distributions. Okay, have a nice weekend, and don't forget the homework. It's due every week. It is the exam. You are doing the exam. There is no other exam. If you miss the homework, then that means you are losing points on an exam. So please do the homework on time. Okay, see you later. Bye.